Okay, today we will start talking randomization tests. Randomization tests are a way for us to conduct hypothesis testing from a computational standpoint, okay? And so before we get into that, we got to do a little bit of review here, and we'll talk about hypothesis tests in general. You know, one of the prereqs for this class is Stats 10, but then I've learned quite often that many students have not taken Stats 10, or they took some kind of stats class at maybe a community college or in high school or something, and just, you know, their understanding of hypothesis tests might be a little bit incorrect or whatnot, and so I will try to just hash out, I don't know, an entire quarter's worth of hypothesis testing material from Stats 10 in like a few slides here, and if any of this doesn't make sense to you, please ask questions, and we'll get through this. Okay. So in your intro stats class, I'm pretty sure you would have covered hypothesis testing, yeah, and very central to that is the setup of the null hypothesis and the calculation of the p-value, okay? And generally, you set up the null hypothesis in such a way that you say that there is no significant difference between the specified populations, and any difference that we do observe in our samples is due to just sampling error or experimental error. So these are just results of our sampling process, and not that the populations themselves are different, right? Because in hypothesis testing, what we're trying to do is we are trying to make a conclusion about everybody in the population, which is just too many people for us to observe directly, and we're trying to make a conclusion about everyone even though we've talked to only a small sample of people. So it's trying to make a conclusion about everyone in the United States, even if you only look at a sample of 100 people or 50 people or something like that, okay? And on the other hand, we have the p-value, and the p-value is the kind of the quantity that we get after we do a bunch of calculations and whatnot. And the definition of the p-value is it's the probability of obtaining a result equal to or more extreme than what was actually observed. So you summarize your sample with a sample statistic or a test statistic, and you want to know what is the probability that a random sample would produce this, okay? And that probability is the p-value. It's the probability of obtaining a result equal to or more extreme than what was actually observed when the null hypothesis is true. Okay, so just kind of a quick review. Let's say we've got population 1 and population 2, and we might say the null hypothesis is that they have the same mean value. So it could be something like population 1 is California and population 2 is Texas. And somebody says, you know what, I think in Texas, the students have better reading scores than the students in California. And, and we say, I don't think so, or whatever. And so we start off with the null hypothesis that the reading scores, the average reading score for all students in California is equal to the average reading score for all students in Texas. That would be the null hypothesis. We are talking about the entire populations of California and the entire population of Texas. Okay. Of course, we can't study everybody in the entire state, so you collect data, you get a random sample, and your sample mean, we'll say population 1 will be California. The average reading score in California is 10, and then the average reading score in Texas is 12. Okay, X bar 1 is 10, X bar 2 is 12. And then somebody goes, look, 12 is bigger than 10. It's 2 points bigger than 10. Therefore, Texas has higher reading scores on average, okay? But as we learned in our intro stats class, that difference of 2 points may or may not be statistically significant, okay? We might want to say, is that difference significant? And the answer is, as always, is it depends, okay? And it depends on the standard error. It depends how much variation we see in the numbers itself, okay? And so one possibility is that the standard error is very small. And so this observed difference of 2 could be much larger than the standard error, say 5 times bigger than the standard error, okay? And in that case, a difference of 2 would be something significant. So the standard error is kind of a measure of the variation of our sample statistic, okay? And so you know, that might mean if we took another random sample from California, maybe we get 10.1 or 10.2 or something, and a random sample from Texas might produce 11.9 or 12.1 or something, meaning there's not a whole lot of variation from sample to sample. Okay, that would be a small standard error. On the other hand, the standard error could be large, okay? So if we took another random sample from Texas, maybe that average score is not 12, but the average score is 10.5. And if we took another random sample from California, maybe that average score won't be 10, but it'll be 11.5 or something, okay? There could be quite a bit of variation in there that would be reflected in the standard error, and we might find that this difference of 2 points, 12 minus 10 being 2 points, that could only be maybe 1.2 times bigger than the standard error, okay? And in that case, this difference of 2 points would not be significant. And I'm sure in your intro stats class, what you should have done is you've learned how to calculate these test statistics. Most likely, in this case, you would have learned a t-test, and the t-test would be, you know, x bar 1 minus x bar 2 divided by the standard error. Standard error is, you know, square root of s1 squared over n1. You probably know, right? So I'm hoping this line of thinking and reasoning is okay, reasonable, familiar. Okay, and then and this leads us to p-values. Okay, so rather than just saying that difference of 2 points is large or small compared to the standard error, we will quantify this amount using a p-value. Okay, and again, the p-value is the probability of observing our data, or something more extreme. In this case, it's the probability of getting a difference of 2 points or something bigger than a difference of 2 points if the null hypothesis is true. Okay. If our p-value ends up being small, it means that the observed difference that we got, that difference of 2 points, is so large that it's very unlikely that random sampling would produce a difference of 2 points. Okay. And therefore, the fact that we did observe a difference of 2 points tells us that our data is not just a result of random sampling, but rather a result of the null hypothesis being wrong. On the other hand, if the p-value is large, it means that the difference that we get could be a result of random sampling, and we don't want to kind of just discount that possibility. Okay, so we are unable to disprove the null hypothesis, but at the same time, it does not prove that the null hypothesis is true. The key thing in all of those tests was kind of the use of the t distribution, or the normal distribution, in your intro stats class. And that depends on something called the central limit theorem, which basically says that the sampling distribution of a sample mean follows the normal distribution. And you probably learned that there were some conditions that had to be true in order to use the central limit theorem. Things like the samples had to be large, the samples had to be drawn independently and randomly from the population, things of that nature. And that is what allowed you to use the normal distribution and its cousin, the t distribution, in order to calculate p-values. And so those tests are known as parametric hypothesis tests because they depend on a distribution that is defined by parameters. Okay, you probably had to prove the central limit theorem or at least derive the central limit theorem in your 100B class, maybe. That's what we have. Okay. The alternative that we can do is a randomization test. And in a randomization test, we do not use the central limit theorem, okay? We don't depend on any kind of distribution for the sample statistic. We just say the critical assumption we depend on is what we call exchangeability, okay? The null hypothesis will still be the same. The null hypothesis is that there's no difference between the two group means, no difference between the means and the population. But we're not saying that X bar has to follow a normal distribution. Okay, that was a key thing in the central limit theorem, but for randomization tests that is no longer necessary. Instead, we depend on this assumption of exchangeability. Okay, I'm going to just pause here, and I want to make sure the review so far of hypothesis testing from kind of your intro stats class was okay. All of this talk about the central limit theorem and also makes sense. Okay, it's hard to read everybody's faces here, but that's what we're going to do here. Is we're moving forward, and we're going to say we have data. I don't want to assume that the central limit theorem holds true, or we don't want to do it from a kind of this analytical perspective, and so we're going to do it from a randomization perspective here. All right, so what is this thing of exchangeability? Okay, we're going to take another step back and talk about data collection, right? So in statistics, what are the kind of our two big sources or two primary ways of having data to work with? One is the controlled experiment, and the other would be the observational study, right? Okay, so we got the controlled experiment, we have the observational study, okay? What's the key difference between the controlled experiment and the observational study?
And when we assign the treatments.
Yeah, in the experiment we assign treatments. Observational study we do not, okay? And because in the observational study we do not assign treatments, and in the controlled experiment we do, what's the key difference as far as the conclusions you can make? Yes, a causal conclusion. You can only make cause and effect conclusions from a controlled experiment if your experiment is done correctly and the data support it, whereas in an observational study, we can never make a cause and effect conclusion. At best, we can say there is an association between the outcome and the kind of the predictors. There's a whole subfield of statistics known as causality research, which tries to get things very close to a cause and effect outcome from an observational study, and it's quite an interesting field. But in general, the over the wide sweeping paintbrushes are controlled experiments. You can make a cause and effect conclusion. Observational study, you can't. Okay, there's a lot of work being done in trying to make cause and effect conclusions from observational studies, but it's very difficult, and you can devote your career to studying that. Okay. So how we obtain the data matters and influences the kinds of conclusions and the kind of tests that are appropriate here, okay? So let's say we have some kind of study we want to do. It says, suppose a dentist wants to know if a daily dose of 500 milligrams of vitamin C will result in fewer canker sores in the mouth than taking no vitamin C, okay? So sometimes people get canker sores in their mouth, and we want to know if taking vitamin C will reduce that. Okay. So here is scenario 1, right? Okay, so the dentist, working through the local dental society, convinces all of the dental patients in town with appointments in the first 2 weeks in December to be subjects of a study, all right? He divides them into 2 groups, those who normally take 500 milligrams of vitamin C each day and those who do not. And then he asks them how often they have canker sores in their mouths and checks their dental records to see who has complained of canker sores. He compares the proportion of those who take vitamin C and complain about canker sores with the proportion of those who don't take vitamin C daily and complain of canker sores. And at the end, we find there is, I had this written wrong, but there is a significant difference between the 2 proportions, okay? Where those taking vitamin C have significantly fewer canker sores than those who don't. All right, what can we conclude? So is this an observational study or a controlled experiment? Okay, observational study. And do we have a random sample or not? We do not, okay? So the way we selected our patients was that we took patients who had appointments in the first 2 weeks in December. This is from last quarter. I should change this to April or March. We just took patients who had appointments in the first 2 weeks of the month, and that's not going to be a random sample, right? So it's not. We're not going to be able to make any kind of conclusions from this population or from this sample that can generalize to the greater population. Okay, we might be able to make some kind of crazy assumption and say the patients who do have appointments this month are representative of the general population, but that's a risky assumption to make. Okay, we don't know that. Okay. Also, it's an observational study. We did not tell who's going to take vitamin C and who won't take vitamin C, and so we cannot make cause and effect conclusions. So at best, all we can say is we know that for these patients, those who take vitamin C have fewer canker sores than those who don't. Okay, we don't know why. We don't know if it's because of the vitamin C or not. Okay, and we don't know if this result would be consistent or could generalize to another group. So it's not that great of a study, okay? Scenario 2, okay? We're still going to select patients who have appointments in the first 2 weeks of the month, okay? Then we randomly assign half of them to take vitamin C, and the other half we assign them to abstain from taking vitamin C. At the end of the study, we find that there is a different proportion between the 2 groups, and those who take the vitamin C have fewer canker sores than those who don't. So what can we conclude this time? Okay, so once again, we do not have a random sample, so we can't generalize to a larger group, but the treatments were randomly assigned, okay? So assuming everything else was kind of controlled or randomized or factored into, the difference in proportions in canker sores can be attributed to the taking of vitamin C. So, but we do not know if this result would be consistent with another group, but we do believe that we know why for this group that the proportions differ. So we're going to say that we're going to conclude that the proportions are different because of the taking of the vitamin C, but that conclusion applies only to this group. Okay. if we continue on here, we're taking a random sample of dental patients in town, and we convince them to be part of our study. Then we divide them into two groups, those who normally take vitamin C and those who do not. We compare the proportions. And so here we have a random sample, but not random assignment. Okay? So in this case, the patients that were selected are a random sample of dental patients in the town, so that whatever conclusions we make here could then be generalized to the population, which is all dental patients in the town. Okay? It's not all people in the town. It's only people who are dental patients, because that's the kind of the sampling frame from which we selected patients or selected participants. And then it only generalizes to this town. We don't know if it can generalize to a larger group. We might be able to make the assumption that the people in our town are representative of the entire country. That might be true, that might not be true, we don't know. And in that case, then we might be able to generalize to a larger population. But again, so the study was observational, so treatments were not assigned randomly. Okay, so we cannot make a cause and effect conclusion. So all we can say is, for the population of dental patients in this town, we know that those taking vitamin C have fewer canker sores than those who don't, but we don't know if it's the vitamin C that reduces the canker sores or if it's some other confounding variable. Okay. And again, we cannot conclude for the general population taking vitamin C, those who take vitamin C have fewer canker sores than those who don't, because we were only looking at dental patients. And again, we don't. If dental patients in this town are representative of dental patients in general, then we might be able to expand this to all dental patients in general. But if not, that would be a bad assumption to do, right? So, when you read a study and it says, we did this study in, I don't know, the state of Ohio or the state of Iowa or something, you have to ask, does this state of Iowa look like the entire country? Maybe, maybe not. I don't know, okay? And, if you read medical research articles, a lot of the time, the patients who participate in these things are white males, and it's hard to know if the results that happen to the participants in this study will generalize to people of other races or genders, and it's hard to know. We don't know, right? And if they did it on a certain age group, then it's also difficult to know if it will generalize to everybody else. And so this is just something that we have to keep in mind, okay? A lot of times, what happens to one human can happen to many other humans, but sometimes just genetic, ethnic, and just differences are enough to make a difference in the resulting study, and it's very difficult to kind of parse everything out. So what's a representative sample? We don't know. All right, and then lastly, scenario 4, we've got a random sample and we got random assignment. So what can we do? This is the heroic case study, and so because it was a random sample, we can generalize to the population of all dental patients in the town. Because we did have random assignment of the treatments, we can make the conclusion that the difference can be attributed to the vitamin C, and that's what we have. Okay, so if we want to make a cause and effect conclusion, we need random assignment. If we want to generalize to a bigger group, we need random sampling. Okay, is that all right, this review here? All right, so let's go back to randomization tests and this concept of exchangeability. Exchangeability is the idea that under the null hypothesis, all possible permutations of the data are equally likely. This is an important definition, okay? Or that any permutation of the data is exchangeable with any other permutation of the data. All right, what does this mean? Practically speaking, this means that this assumption of exchangeability applies to experiments where random assignment has been used. Okay? So, for example, you can imagine you have a sign-up sheet of people who want to participate in your study. Okay, you have a sign-up sheet, 50 people say, I want to participate, and they show up, okay? And then you randomly assign them, I don't know, maybe you have a deck of cards, okay, and you shuffle them up, and you say, so we'll say we have 52 patients, right, who've signed up for your study. You have a deck of 52 cards, and then you shuffle them up, and you deal them out, and you say, if you have a red card, you're going to be in group A, and if you get a black card, you're going to be in group B, okay? And so, when you deal them out, you're going to get a certain set or a certain permutation of your data, okay? However, if you shuffled the cards one more time, you would get a totally different random assignment, right? However, that random assignment is just as valid as your current random assignment, okay? And so this concept of exchangeability is that under the null hypothesis, when, as far as kind of the random assignment goes, if there's no difference between the two groups and who's going to end up getting what, every single possible permutation of the data is equally valid. Okay? This cannot apply if there's not random assignment but just random sampling, okay? Because when we do random sampling, we're not going to get the kind of just different permutations of the data here, okay? So if if the patients are assigned treatments randomly, then any arrangement of patients is equally likely. And in cases where treatments were not assigned randomly, such as an observational study, then the permutation of the groups are not equally likely. Okay, so if we're doing an observational study, and we said, not based on whether you got a red card or a black card, but we're going to split you up into groups based on some trait that you have, prior to entering, signing up, such as, we're going to split you based on gender, or we're going to split you based on whether you're taking vitamin C or not vitamin C, then every permutation is not going to be equally likely. So exchangeability applies only when you have random assignment. Okay, I'm going to show you a video now from Mythbusters. They used to have this video on the Discovery website, Discovery Channel website, but they took it down, and so I had to spend $2 of my own money to buy the Mythbusters episode. So anyway, and then, okay, I'm going to put a break in the video here,